You can set up stationary sound waves in a pipe that's open at both ends, and this is the panpipe situation. If you're familiar with panpipes, you'll know that the length of the pipe determines the note you hear when you blow across the top, and we can explain this using stationary waves. Now, whereas in the stationary waves on a string situation, I think it's quite obvious that there have to be nodes at both ends because we can see that the string is fixed at both ends. I think it's a lot less obvious, or not obvious at all, that in the open pipe situation, you need to have antinodes at both ends. Okay, and sound waves obviously are longitudinal, and so what I've tried to show this here by how we normally do it. You've got the particles bunched up in the middle there at where the node is, and then they're spread out and maximally spread out at the ends where the antinodes are, but that's not a very clear way of showing it. So we typically always represent the longitudinal wave by drawing it as a transverse wave instead. Okay, so this is the lowest frequency of sound wave that will cause a stationary wave inside the pipe. And that's because we've got an antinode here, an antinode here, and as few waves as possible in the middle. And this is once again called the fundamental frequency. And if we just turn it on its side there, I think it's a bit easier to see that what we've got is half a wave there, half a wavelength. And then these are the next two patterns, and turning on the side again, so we can see, so that was half a wavelength. Here we've got two halves, and here we've got 1, 2, 3 half wavelengths. And so we can see that the rule is actually the same. You will get a standing wave in the pipe if the length of the pipe is equal to a whole number of half wavelengths. So it's actually the same rule as we had for the stationary wave. Why? Because in this situation we've got antinodes at both ends. In this one we had nodes at both ends, and so that actually results in the same rule. And again, the wavelength of this one is half that of this one, so the frequency will be double because the speed of sound will be the same in both pipes. And here, if you convince yourself, this wavelength is a third that of this one, and so the frequency will be 3 times the fundamental frequency. And so this is the note that the panpipe will play if you blow across the top of it gently. If you blow really hard, you might be able to get the next harmonic, but this is typically the one it's going to play. So we could work out what note that will be. So I'm going to say, let's say I've got a pipe that's 10 centimetres long. Well, for the fundamental, that means I've only got half a wavelength in there. So that means that the 10 centimetres is half a wavelength, and the wavelength is 20 centimetres. Now the speed of sound in air is about 340 metres per second. There's my wave speed equation, and rearranging my frequency is going to be this. And putting my numbers in, I get about 1700 hertz. And that is about the A, nearly 3 octaves above middle C. So that's the note that a 10 centimetre panpipe will play.